All right, here we go. We are about to start in calculus with trigonometry. We should be on page 208 or so of your workbook, depending on which version of the workbook you have. So we will be beginning with this. We actually are not going to get into derivatives quite yet. We're going to start off with kind of a different topic that we're going to need this for some other stuff in trigonometry, but we'll start into derivative things tomorrow and differentiating tomorrow, the next section, and we'll start differentiating that. This starts off with just looking at some limits. And this starts off with our graph of y equals sine x. And it starts by saying, okay, so from our graph, determine the limit as sine x is as x gets closer to 0 from below. So remember that's what are we getting closer and closer to as we get closer to 0. And the sine of x as we get closer to 0 from below is 0, from above is 0. And so in fact, our limit as x goes to 0 is 0, not a big deal. For cosine, as x gets closer to 0 from the left side, this is getting closer to a height of 1. And same thing from above. As we get closer, this is a height of 1. So we have our limit of cosine as x gets closer to 0 is equal to 1. What we're wanting to get at with this idea is we have kind of a different looking limit here. Important in calculus is the limit of sine x over x as x gets closer to 0. Our graph looks kind of like this. And if we use our table of values below, if we look at sine x divided by x, if we take negative 0.1, we get 0.9983. As we get even closer, 0.9999. And then as we get closer still, more decimal places by 9. Now keep in mind, when x gets closer to 0, this is undefined. When x gets closer to 0, sine of 0 is 0. So what we're getting to as we're taking this limit, it's getting closer to, we have 0 over 0. Now 0 over 0 is indeterminate. We can't just say that that's equal to 1 or infinity or 0 or any kind of number. We don't quite know what it is. But we do suspect by going through this, that going at this, looking at this, what x gets closer to 0 from the left and x gets closer to 0 from the right, we're getting very, very close to a y value of 1, 0.9983 for this one. And so we seem to be getting closer to 1, but not quite sure why. When you take calculus in university, you're going to look at this from a different approach, and you're going to use some different methods to look at this and consider why exactly it's equal to 1. But for now, we're just going to kind of notice that even though the limit is 0 divided by 0, we can't say, oh, anything divided by itself is 1. That's not the case for 0 over 0. 0 over 0 is indeterminate. But in this case, we actually can. So you're going to get into university and you're going to start to look at some different approach to this. But for now, let's just look at the fact that it is equal to 1. Even though f of x is undefined and doesn't exist at x equals 0, sine x over x as x goes to 0 will equal 1 as a limit. And in fact, if we have any multiple of x, so if we have sine kx divided by kx, that will also equal 1. So if we have sine 3x over 3x, that would just be equal to 1. So what can we do with something like this? Well, we can take sine x over 4x. This isn't going to work with the 4 in there. And so if we break this apart and call this the limit of a quarter times sine x over x, as long as we can get this so it's going to look just like this, sine x over x, then we have that factor like that. When we started this course and we first started looking at limits, we said, okay, the limit of a constant times another function is going to be equal to the constant times the limit of that function. And so we can, essentially, we're pulling 1/4 outside of the limit. It doesn't have an effect on what the limit is. So we bring that 1/4 out front. This is 1/4 times, this just ends up being equal to, because of this is just 1/4 times 1. So what we're doing here in this section is we're just massaging these to kind of try to make something look like this so we can evaluate that limit by this magical property of that this is equal to 1 through this. Okay, so if we have in number 2, we have the limit as x goes to 0 of negative sine 3x. So this is going to work for us if we have sine 3x in the numerator, and then if we have 3x in the denominator. We don't. So what we're going to do, we're going to do 2 steps. The first step is let's factor that negative 1 out, pull it outside of the limit. The other thing that we're going to do is we are going to multiply this by 3 over 3. Of course, we can do that. That's just 1. And so if the numerator 3 we pull out of this limit, so negative 1 times 3 times the limit as x goes to 0. If that numerator 3 comes out, this denominator 3 stays in here, and we call this the limit of sine 3x over, now we have sine 3x over 3x, the limit of which is equal to 1. Number 3, sine of 2x over 3x. So it's just going to be a little bit of massage that we're doing here. We want this to say 2x. It doesn't. It says 3x. So what are we going to have to do? Well, we could take the limit as x goes to 0. So we know that this is sine 2x. We know it's dividing by 3x. We want it to divide by 2x. So we're going to multiply this by 2, but we can't just multiply that by 2. We have to multiply the numerator by 2. So this ends up being equal to the limit as x goes to 0. So now what do we have here? We have sine 2x over 2x. But we also have this new 2 in the numerator. We also have that old 3 in the denominator. And this is equal to 2/3 times the limit as x goes to 0 of sine 2x over 2x. This is equal to 2/3. This goes to 1. This becomes 1. We're left just with 2/3. Number 4. There's some other things that we know that that's going to be relevant here. We need to remember our Pythagorean identities from 30-1. 1 minus cos squared. Because cos squared x plus sine squared x is equal to 1. That's your basic Pythagorean identity. Therefore, 1 minus cos squared is equal to sine squared x. This property that we are using in this unit here, this property that we're using in this lesson just only works with sine. So sine x over x is what we're taking the limit of when x goes to 0. That will equal 1. We don't know anything about cos x over x. Actually, that's not true. As cos goes to 0, the numerator goes to 1, the denominator is going to 0, so that would be infinite. So I suppose that one's not even a problem, but let's just work with this with sine so we can figure out what's going on with this. This ends up being now the limit as x goes to 0. This is sine x over x times sine x over x. So just breaking that apart. And that, of course, is equal to the limit as x goes to 0. I'm really kind of baby steps through this by doing it this way, by breaking this apart into 2 limits. But your professor next year will probably want to see this. So we have a limit that's equal to 1, another limit that's equal to 1, and there it is. I suppose perhaps before I move on from this, let's just look at that. Like, what would be the problem with evaluating it like this? If I've got the limit as x goes to 0 of 1 minus cos squared. If I break that apart into two limits, this is the limit of 1 over x squared minus the limit of cos squared over x squared. And if I look at those as two separate limits, well, as x goes to 0, this is infinite. And then as x goes to 0, cosine x squared over x squared is 1 over 0. So it's infinity minus infinity, which means what? We don't really know. We got to be careful. We can't be really messing around with infinity as an algebraic, as a numerical item. It's not a number. And so we can't really arithmetic with it. And so because of that, this whole process kind of falls apart. And that's why we look at it as a function of sine. All right. Number 5. Limit as x goes to 0 of cos x minus 1 over x. So again, we don't really know much about what's going to go on with this. We can't deal with it as cos. And so because of that, let's see what else we can do. Again, the fact that we know that cos squared x plus sine squared x is equal to 1. We have your Pythagorean identity from 30-1. We also know that cos x minus 1 isn't really part of that because it's got to be squared. But what we do know that we can do is we can always multiply this by cos x minus 1 over x. If we multiply this by cos x plus 1, we multiply by its conjugate, that's going to be helpful for us. Because as x goes to 0, what's cos x minus 1 times cos x plus 1? If we multiply those together, those of course are cos squared x minus 1 over x bracket cos x plus 1. So multiplying by our conjugate, we create in here cos squared x minus 1, cos squared x minus 1, just considering what this would look like. That is negative sine squared x. Right now, this is dividing by x. It's also dividing by cos x plus 1. I'm going to write that over here. I'm just going to separate them as a product. Doesn't quite work for us. What are we going to need still in here? Because this is sine squared x. That's sine x times sine x. We're going to need another factor of x in here. So let's multiply this by x over x. All of that aside, this ends up being the limit as x goes to 0 of sine squared x over x squared times the limit of, what else do we have left behind? Negative x over cos x plus 1 as x goes to 0. This first part, this is what we've been doing in this section, that's equal to 1. What's the rest of this? This is, upstairs we have 0, or negative 0 if you want, over 2, which is equal to 0. This last one, kind of interesting. A couple different ways of looking at it. One way we could look at it is we have this pi minus x in the denominator. And so let's make an aside here. We don't do this very often in math. We like to kind of work linearly, if you will. But if we have pi minus x, we don't have sine of pi minus x in the numerator. If we did, we'd be done. But what do we know that that looks like? If we think back to 30-1 and we have your sum and difference identities for trigonometry. This is equal to sine pi cos x minus sine x cos pi. And if this is equal to, so we have to realize what's happening at pi. Sine of pi is equal to 0 times cos x. Sine of x times cos pi. Cos pi, cosine of pi is -1. So this ends up being 1 sine x. So therefore, sine of pi minus x is equal to sine x. So therefore, our original question, the limit as x goes to pi. Notice that x is going to pi, which means that denominator is going to 0. And if our original question said sine x over pi minus x, so that's our original question, now we can state that this sine x here is actually equal to sine pi minus x over pi minus x. So we've created this. The sine of this piece that's going to 0, that denominator is going to 0. There's our rule for this section, that this ends up being equal to 1. I suppose another way of looking at it is this. Another way of realizing that this is going on, that sine of pi minus x is equal to sine x. If we think about this, here's pi. Here's pi as an angle. If I take pi as an angle and subtract x as an angle, if I subtract x radians, what this is saying is if I start from 0 and I add x radians. So as I'm going around my circle, here's pi. If I subtract x, that's this angle here. The sine of it is the height to that point, right? The sine is the y. And if I take that same angle x and start from 0 and start to go in a positive direction, it's going to be at the same height as this point. And so the sine of this angle, pi minus x, the sine of that angle will equal the sine of this angle because they are at the same height. And so therefore, sine x is equal to sine pi minus x. And we could substitute that in here and create this. Whew, lots going on with that. Think about it just before you go to sleep tonight. Maybe in the morning it'll all come. It takes some time to get your head around that, absolutely for sure. Anyway, that's it for this section. When we start into the next trigonometry stuff, we're going to start getting into differentiating that, and that will be it. Thanks so much. Good luck.